There's a little difference in thinking. I'm going to go the change in gravitational potential energy of objects near stars in stellar metamorphosis. With a few simple statements, it is outlined that the gravitational potential energy of objects near stars in stellar metamorphosis changes as the star evolves. Explanation is provided. In stellar metamorphosis, exoplanets are evolving, and dead stars. They have lost the majority of their mass, and their gravitational fields and radii have diminished considerably, as well as the rate of acceleration with free fall of objects in those gravitational fields. Therefore, as a simple rule, the gravitational potential energy of objects in highly evolved stars such as Earth is much lower than in younger stars such as the Sun. And here's the equation for that. Gravitational potential energy in joules equals mass times acceleration of free fall times the change in height. Now, the only thing I'm really supposing here is that you put a variable as in change in or delta where the acceleration of free fall is, because as well the mass changes too, and that would be actually the mass wouldn't change because this is the object that's actually dropping and going towards the surface. So the only thing that would be the delta G in the middle, which would be the acceleration of free fall. Of course, that would be reliant on how much mass is lost from the star itself, not the object it's falling. And here it says, for a 1 kilogram object dropped on Earth, which is about maybe like 8 or 9 cheeseburgers, with an acceleration of 9.8 meters a second squared at 1,000 meters, subtracting for loss due to atmosphere causing friction, has a gravitational potential energy, or GPE, of 9,800 joules. For the same height, the GPE for a 1 kilogram object dropped in the Sun would be 275 meters per second squared acceleration of free fall. Subtracting for loss due to atmosphere causing friction and other factors is 275,000 joules. So all that energy of those falling cheeseburgers will make one hell of an impact. What this means is that the potential energy for objects that fall on younger stars that have a lot more mass and have much higher accelerations for free fall is much higher. This means their atmospheres are probably much more energetic from the heat of friction of particles constantly falling back into the star. It should be no wonder why young stars are bright and hot. The particles that fall back into the star are accelerating extremely fast at an astounding 28 Gs. To compare familiar objects, a 50 kilogram dumbbell dropped at 10,000 meters from the surface of the Sun would have about 137 million joules of kinetic energy. That would be the same energy as a 60-ton aircraft on Earth landing at speeds of 115 knots. So imagine like a 100-pound dumbbell that you see at the gym that basically nobody can lift up unless you're a strong man, being thrown off of Mount Everest. And the force of that hitting the ground, minus the friction from the air, would impact, if that same object was on the Sun, it would impact the same energy as a landing aircraft on the Earth. That's incredible. Big difference here. So it is clear for the reader the GPE of objects inside or near stars diminishes at a smooth, continuous rate, given the change in height from the surface and mass do not change, and levels off as the star begins completely solidifying and has lost about 99% of its atmosphere. So to rewrite this equation, it would be to add delta in front of the G, so it would look like that. You guys see that real quick? Right there. And that's basically it for that. A lot of other mathematical equations are going to come out of this theory. It isn't going to be fun. On a lighter side, I found this book at Books A Million. I had this book when I was a child, 10, 11 years old, and when I really liked, finding rocks and minerals on the ground and trying to figure out what they were. Of course, everything was silver and gold to me as a child. I was like, oh, I found silver, I found gold, I found diamonds. Turns out there's a lot more than what meets the eye. There's a lot of different chemical combinations out there. And it also brings back memories of why green is my favorite color, because check out that emerald right there. Now that is something that I would love to have for a collection of minerals. Look how beautiful that crystal is. And that's what got me fascinated with the whole Earth thing to begin with, is stuff like this when I was a child. So I went ahead and bought this book. Of course, nothing's changed in like 30 years. It just keeps on being reprinted with the same information. So when I see all these pictures in here, they look very familiar to me. It's like looking at a time capsule. But yeah, read books like this. You'll see these formations, and they all will be explained what they are: shale, sandstone, eroded sandstones in canyons, limestones, different types of beddings, gypsum rocks, marble, and it'll go over a lot of that, where they're located, you know, where to find them, how to identify them and classify them. Basically, rocks and minerals are the eventual evolutionary composition of a star itself. So when you see a lot of the mainstream media and, you know, Discovery Channel, National Geographic, where they say stardust, we're all made of stardust. Well, essentially the star dust is dirt. We're living on an ancient star older than the sun. So it's the dirt you can pick up off the ground is the stardust. And if you compact it with heat and pressure, you can make rocks and minerals out of it. It's what stars do. They form rocky bodies that are differentiated like Earth. Alright, y'all. Take it easy and read books like this. You can learn a lot of information from them. Alright, later.